So we're going to make a switch now. We've kind of gone through, one-dimensional proton and C13 NMR. We've gone through IR, UV vis, mass spec. And so now we're going to kind of make this circle back to NMR. Okay, so we are going to cover and talk about some two-dimensional NMR techniques now. So we'll start out with kind of an intro here, a little bit of theory. Why isn't that? Huh. There. And then, we'll introduce some experiments, and then we'll start applying. All right? So, what we've learned so far using NMR is it uses radio waves to detect nuclear spins. The type of information that we gain from the spectra, from proton NMR spectra here, was the integration. So we got information about how many, first we get the number of peaks. We can integrate those to determine how many protons are represented by each of those peaks. We get something about chemical shift, tells us about the local environment, adjacent functional groups, things like that. And we got information from splitting to tell us what protons were adjacent. So why do we need more than that, right? So essentially, if our spectrum gets too complicated, right, and we have too many overlapping peaks, we can't see what the couplings are, then we run into problems. And this is where the two-dimensional NMR becomes more useful, because if we take a one-dimensional spectrum that's overlapping, we split it into two dimensions, we can sometimes resolve the peaks. Really, one-dimensional spectra have two dimensions already, right? Because they have a frequency for chemical shift, and they have the intensity for the integration. Really, one-dimensional, when we talk about NMR, means that the pulse sequence has a single time variable. Okay, so that's the dimension. And so here's drawn out what we looked at as a normal pulse sequence for a one-dimensional spectrum, and our time period is this acquisition time. Even though we only have one here, we're calling it T2 because that's what we're going to call it in the next spectrum as well. So remember, we had this relaxation delay just to allow whatever signals to relax into the plus Z direction. We pulsed it, tipped everything down into the XY plane, they process, and we measured the processional frequencies. So for two-dimensional NMR, this is like a simple one, we will have two different time variables. So we have the acquisition time, just like we did before, but we have some additional time variable here. So notice that this one has a relaxation delay, but then it has two different pulses, two 90-degree pulses. Pi over 2 is 90 degree. So both around the x-axis, and it has this T1 value, which is incremented during the experiment. So what we essentially do is we run a spectrum with one value of T1, then we increment that value, we change it, then we run another spectrum, we change it, we run another spectrum. So we run a series of one-dimensional experiments. Depending upon how much sample we have, if we're sample limited, if we have a small amount, then we may need to do multiple scans at each of these increments. So let's just look at what might happen if we do this. Okay, so let's draw this out. So here's our starting point down on the left. We have all of our magnetization in the plus z direction. We are going to do our first 90-degree pulse, which is going to tip the magnetization into the XY plane, like this. And now we're gonna choose an increment, and we're gonna wait that time period, and then we're gonna pulse it again, and then we're gonna do acquisition. Okay, so let's start out with this T1 equal to 0. Okay, so immediately after, so here's the x axis. So this was the 90-degree pulse. It rotated around the x-axis. So we're going to do T1 is 0. We're going to do another 90-degree pulse. Oops. Around the x-axis. So what that's going to do, rotate it around here. So it's going to tip it down into the minus z direction. And then we're going to do acquisition. Okay, so what's our spectrum going to look like if we do acquisition at this point? Nothing, right? Because there's no signal in the XY plane, right? So our spectrum is just going to be a straight, nothing. All right, so we are going to try this again. We're going to do just delta T1 equals, we're just going to say 1. It's something that's non-zero. We're going to, okay, so that is going to allow this signal to precess a little bit. So it's going to be, say, over to here. Right, so it's precessing this way. Then we're going to do our 90-degree pulse. And again, it's going to rotate it around this axis. So here's the plane. It's always kind of hard to draw, but it's going to be somewhere tipped down into this XZ plane, right? And so from there, there's some component that's in the XY plane and some component that is in the the Z direction, right? It's downs. So we're going to run our acquisition. And we're not going to really worry so much about the phase here, but just how much signal is in the XY plane, because we can phase it however we want. Okay? So what's this going to look like? A small peak. Okay, so we're going to see some small peak. All right, so we're going to do this again. 2. We're going to wait some additional time. Let's say that we wait enough time where our signal is precessed over to this x-axis.
So how much is the value of delta T1 and 2, something like that? Depends.
Yeah, I think what happens is when you set it up, so it partly depends on, so one thing you can choose is how many increments in T1 do you want. Mm-hmm. And the increments here, okay, so here, the number of increments really defines our resolution in this T1 dimension. Okay, the resolution in the T2 dimension depends upon how many points we're acquiring in the spectrum, right? And you can set that. But typically we have a lot more resolution in the T2 dimension than we do in T1, because we can, say, acquire 1K of points or 2K of points in T2, but we won't want to do that many increments in T1. Okay? Because it would just take too long. So I think we tell it how many increments, and then the spectrometer kind of sets up how much that time delay is. And probably, I can't remember really, T1, obviously you don't want T1 to increment over a longer time period than T2 is, right? Or you're going to be incrementing out beyond the point where there's any signal left, essentially. All right, so we're going to do our other 90-degree pulse now. And how is this going to change after this 90-degree pulse? It won't, right? Because we're just going to rotate around essentially the axis like this, right? So this is not going to change like this. And then we're going to do acquisition, and how is this going to look?
A lot larger.
Right, it's going to be bigger, right? Because essentially we have all of the signal in the XY plane again. All right, let's just do one more here. So we're going to do delta T1 3, and we're going to wait until, let's say this is precessed over here somewhere. And then we're going to do our 90-degree pulse. Let me move this up just a little. And then that is going to if it's back, it's going to essentially flip kind of up like this, right? Because it's pointing out this way, and it's gonna, when we do the 90, it's gonna rotate up like this, right? Before it was pointing this way, and we rotated down. So this, and it's gonna have some component in each of these directions, right? So then we're going to do our acquisition, and we're going to get a smaller peak again. And I guess we do set the phase, because if we go beyond, like, precessing around 180 degrees, then we're going to end up with the negative peaks. Okay, so let's look at what we're getting when we look at this. So we're really doing a series of one-dimensional experiments, right? This one right here. Okay, so the maximum intensity was when we had the precession came all the way around to here, right? And then we did this, well, I guess that one wouldn't really matter. 90, it's this second one that's the 45. So this one wouldn't really matter.
The second one or the fourth one?
Well, you'll have sharper peaks because of that. Because as you said, the perfect or the one that's on the x-axis is not going to be affected.
Right.
Everything off of that axis.
It's only going to be. It's going to be rotated. Yeah.
So it's a lot sharper.
Yeah. Yeah. So maybe it's not as simple as I was thinking. But, so in general, which one is this? And if we look at that series, let's look here in A, we get some small peak here. It got bigger and bigger, and this was where it was precessed to 90 degrees was the maximum one. It's going to go back down. It's going to go through a 0, negative, positive. So it's just alternating like this, right? So if we look at this from the side, we're going to see something like this, right? We started small, we got bigger, we're going smaller, negative like this. And if we extend this out longer in the T1 dimension, we get something that looks like this up here. And it's getting smaller. Why is it getting smaller?
Because you're waiting longer.
We're waiting longer, and relaxation is going on during this time.
How was, what do we see like the figure in C that it's decreasing?
Mm-hmm.
I didn't understand why it's, I don't know, like that pattern.
Well, during this time, so if we just did this, well, it's because as we're waiting and as this experiment is going on, we have this T1 and T2 relaxation modes going on at the same time, right? So some of it is relaxing up into the Z direction. That was the T1, and T2, remember, is fanning out into the XY plane. So those are happening at the same time as we're waiting during this increment and everything. So that's why we get a loss in intensity. But this one in B down here is kind of showing that we're actually, measuring these discrete points. And that's what the curve is from these points. Okay? So what does this look like if we have this relaxation? What does this figure here start to look like? The FID, right? The free induction decay. And this is what we got, that we did the Fourier transform to get each of these, right? So now what we do is we essentially, so this looks like the FID. And so we essentially take this and we do a second Fourier transform. Okay, so we get a spectrum in a second dimension. All right, and so this is something that we might look like. So we get the second dimension. So again, we have two frequency axes now, because when we do the Fourier transform, we go from this time domain that we're actually acquiring points to the frequency domain. So we have this precessional frequencies that we're measuring. Okay, and so now we go to the frequency domain. We have F1 and F2. So F1 comes from T1. F2 comes from T2. All right, so T2, remember, this was the acquisition time, and T1 was the increments. Right? But like we, as in one-dimensional, we said actually there's two-dimensional, so this is two-dimensional because there's two axes, there's two time delays or time increments, but we have the intensity as well. Okay? So typically, we don't look at the spectrum like this. I remember always seeing spectra that are kind of looked at an angle like this, and they look kind of cool, but they're not very useful, right? So what we actually do is we look at these spectra from above, and we get contour plot, like a topographical map, right? So we have now our F2 and our F1 axes, and then we have our peak, and we have contour lines. So the more contour lines, the taller that peak is. Notice it's not completely symmetrical, and that just, I think, has to do with noise and things like that. Okay? And so this would have, some frequency value in that dimension and some frequency value in this dimension, right? And if we're only looking at a single line, then these two frequencies would be the same. Okay? So that's kind of the really basic kind of experiment. So we are going to split our experiments into kind of two categories. The first category is called homonuclear. So we're going to see coupling between two of the same type of nucleus. Okay, so these can either be between two protons, or we could do it between two carbons. Okay, so we have a list of types of experiments for each of these, and we're going to do in some of these, a little bit of a historical look at it, to see what types of experiments were first developed, and then look at the ones that are being used more currently. Okay, so our proton-proton experiments are going to be these here. So the first set here is all just coupling. There's one called a nosy. There's another one. So they always have these kind of funny names. There's another one called rosy. These experiments are NOE experiments, so nuclear Overhauser effect. So remember, those experiments show through space interactions. And then there's this C13 experiment, which is kind of cool, but it's not used very often, really, largely because C13 natural abundance is so low that to do this you need two C13 atoms next to each other, and so the statistical chance of having that happen is even way lower. Right, so it's very insensitive unless you have some sample that has C13 labels in it. Okay, so the second type of experiment are the heteronuclear experiments. And so we're going to look at proton and C13. You could do, proton and N15, or you could do other, NMR active nuclei in here as well. So we can look at one bond couplings. Okay, so these are going to be experiments where we're looking at the coupling of a proton directly to a C13 atom. Okay, so this is going to tell us which protons are attached to which carbons. Okay, we have 3 experiments here, and they are kind of 2 different types. The het core was kind of the first one, heteronuclear correlation. And this was C13 detected. So we have 2 different types of nuclei, so in theory the acquisition could be either on the proton frequency or the C13 frequency. Okay, so the first experiments had the detection on the C13 frequency. And we'll talk about why that was and stuff when we get there. This HMQC and HSQC, these are proton detected, which was at the time was oftentimes called inverse detection, just because C13 detection was done first. So inverse was the switch of that. Okay, so there's another experiment here we'll look at is for multiple bond correlations. And so these can be typically either 2-bond couplings, so CH, or 3-bond couplings. You might even see 4-bond if we have like aromatics or things like that. But these type of experiments are really good. So what we're seeing here, so 2-bond, right, would be something like this.
The carbons must be C13 or doesn't matter?
Well,
Carbons for multiple bonds.
Well, it has to be a C13 here.
Oh,
right. So the one that you're coupling to, right? It doesn't have to have all C13s, but just the one you're coupling to. So we know that there's like a 0.1% chance, a 1.1% chance that that peak will be C13. So this is J2. J3 would be something like this, right? 1, 2, 3. So this is 3. So this is going to be really useful if either this, for example, is a quaternary carbon. You know, if there are protons on all of these carbons, we could probably see it by proton coupling, right? But if this is either quaternary, this one here, let me use this green, or if we have a situation where we have, say, a carbon here, and then we have some heteroatom, carbon or oxygen or nitrogen or something, we can see coupling past that heteroatom. Okay, so those are the points. This really becomes useful. So usually what we do is we use the homonuclear experiments and we look for proton-proton coupling. We can use the heteronuclear, the 1-bond experiments, then to see which of those protons that we looked at in the homonuclear, what carbons are attached to those. So we're kind of building up fragments, and then we can hook those fragments together using the multiple bond experiments.
In the multiple bond experiment, can we have another heteroatom attached to hydrogen or not?
So whether this is a heteroatom here, possibly, but we know like if this is an OH, we oftentimes don't see coupling to that because we have exchange, and even NHs, sometimes it kind of depends. If those easily exchange, even like an amine, it doesn't typically show much of this coupling. If we have like an amide, though, that doesn't exchange as easily, sometimes we can see that kind of coupling. Okay? All right, so let's look at the homonuclear experiment. So the first one we'll look at is this COSY. So this stands for correlation. So correlation is kind of a term for coupling. So this is correlation spectroscopy. All right, so this is a spectrum here. So we have 2 dimensions. Again, we have F1 and F2, all right, which come from time domains T1 and T2. In this spectrum, we have 2 different frequencies, okay? And so we see 2 in both dimensions. So the way that we usually look at these is along this diagonal is really the one-dimensional spectrum is along the diagonal. and each of these peaks will have chemical shifts in each dimension. This one has frequency x in this dimension, frequency x in this dimension. Okay, so the diagonal is going to be where we have each of these peaks has the same frequency in both dimensions. Okay. So if we just have a bunch of single peaks like this, it doesn't really help us that much. So I guess the other thing is that typically these spectra that are drawn on each side were called a projection. And what the projection is what we see when we look at the spectrum from the side. Okay, so we could look here, projection, and we would see these two contour peaks looking at it from the angle. Okay, so that's what was technically what we used, but typically now we just plot the one-dimensional spectra on the sides. Okay, so when we would run this, if this was a proton-proton coupling, we'd always run a proton NMR spectrum first, and then we would just take that spectrum and we'd have it plotted along the edge here. And the reason we do that is because the projection typically has fewer points in it and less resolution than the one-dimensional spectrum would have. Okay, so it's going to look a lot more chunky than our one-dimensional spectrum would. Because for example, if we run this cozy spectrum, we might have 1K or 2K of points in our acquisition domain, but when we do a one-dimensional proton spectrum, we'll have 16K or 32K in our acquisition. Okay, so we're going to have a lot more resolution in our one-dimensional spectrum than we will in our two-dimensional spectrum. Okay? So it doesn't really matter if they're just a couple of singlets like this. So it doesn't really help us if we just have single peaks like this. Where it helps is when we start to have coupling. Okay? And so this is a spectrum where we have, this is an AX spin system. Remember, that means we have two peaks that are far apart, but they're coupling with each other. And so this is what we saw for the one-dimensional. These two are coupling with each other, and this is this AX spin system, just two doublets. The way we see it in the cozy spectrum is here's our diagonal. Okay, so this is the one-dimensional spectrum in the diagonal. And we see the coupling between these two peaks as off-diagonal peaks. Okay, so we go from our diagonal here, we can go horizontally till we hit a peak. So this is the off-diagonal. And when we hit the off-diagonal, we can go up. And this off-diagonal peak tells us that these two are coupled to each other. Okay, we could likewise start, at the first peak, and we could go, vertically first to hit this off diagonal, and then we could go horizontally and we get the same information. Okay, so the off diagonal peaks are always symmetrically oriented around the diagonal. Okay? So if we see, typically if we see something that's not symmetrical around the diagonal, it may just be noise. All right? Okay, so let's look at something that would be more useful than just two of these peaks, right? If we have a spectrum with just two peaks, we already know how they couple. Okay, so this is the experiment that we looked at first with two 90-degree pulses. So this is called a cozy 90 because that second pulse is a 90-degree pulse. This additional one. So we have a number of peaks here, and we want to see, well, let's try to assign the peaks to the molecule, if we can see that good enough. So this spectrum here does not include these out here on this ester. But they do include all the peaks around, so from this 2, 3, 4, 5, 6. Okay? So out of those peaks, out of those protons in that spectrum, so what we would have to do is pick out some point to start with, right? So pick out some kind of characteristic peak, just by looking at either splitting or chemical shift or something about what we would expect for one of these protons, and then identify it, to one of these peaks and then work from there. All right, so which of the peaks, protons in here, do you think would be most characteristic, and which one could we assign to one of these peaks along the diagonal? Number 6. Okay, so 6, out here, would be a CH2 group out there, right? And where do you think you would assign those in the spectrum?
The only place with the doublet. So at what? 4.6. Yeah.
Oops, I can't see that. It's blocked by my. 4.6?
Yeah.
So that one has this azide and a carbon on the other end. Do you think that's going to be the most downfield signal?
It's the only one that I would.
And do you think it would really be a doublet?
No, it wouldn't. So that's.
Why would 6 not be a doublet?
Well, there's a lot of chiral centers in the molecule, right? So those would be diastereotopic, right?
Yeah.
Meaning they have different chemical shifts, so they will couple with each other. That would split it into a doublet. And then what else? And be it split again from H5, right? So each of these should be a doublet of doublets. So I don't think that's a bad place to start, but I don't think it's the peak at 4.6.
Is it the one at 3.6?
Could be the one at 3.6.
If we're comparing the two, 5 and 6, 5 would be the more downfield because it's right next to the oxygen.
Right, 5 would be more downfield than 6.
Yeah.
Would 5 be the most downfield?
No.
Oh, what about 2?
2 probably, right? Because 2 is next to the oxygen, but it also, it's hard to kind of see here, but it's also an ester here, so it's also next to a carbonyl.
Okay. I was thinking that was an ether.
Yeah.
Yeah, you said esters.
Yeah. Okay, so I think that we could say that this would be H2 here. And likewise, because H2, because it's an ester on one side, there's the H3, there's only one adjacent proton, so that one should be a doublet.
So sorry, I just missed. Can you repeat it one more time?
Yeah, so because this proton, because there's an ester here, there's no proton on this side,
To be split here.
but there's just one proton over here.
A doublet.
So this should be split into a doublet, right? So that's consistent with this as well. So most downfield, and it should be a doublet. Okay, so that's consistent with this peak that we labeled as H2. Okay, so we're going to start here then at H2. And we're going to look.
Why we're not working with the point at 4.4 and 4.6, the just above the H2?
Up here?
I mean here, just this one. What is this one? Why?
Right, so we're going to start on the diagonal, right? So here's the diagonal.
Oh, it's easy.
And so those ones you were pointing at are off diagonal, right? So what do the off diagonal peaks tell us?
The T2?
No, remember the previous slide. Look at the last slide. What do the off diagonal peaks tell us? Coupling.
Coupling, oh.
Yes. So from H2, we can go either up, just like we did on that last one, till we hit an off diagonal peak. We go horizontal. That means that H2 is coupled to this peak. So what would that next one be?
3.
H3, right? So this is H3. Right? We can do it again. We can go horizontal this time till we hit another off diagonal peak. Go vertically, and we hit another one right here. Okay, there's actually 2 peaks in here, right? So there's this taller one and this fatter one. And if you look carefully at this, notice that this section here has off diagonal peaks going this direction and going this direction, and notice that these are much fatter than this one is here. So that means that this one is going to this peak on the left side, and this fatter one is going to something that's bigger and wider in here. Right, so the size of this off-diagonal peak can tell us how they're aligned together.
That's really nice.
Okay? So that tells us then that H3, so this is going to be H4. So here's H4 up here. And this is where it gets, a little tricky, because H4 is kind of this narrow peak here, but we don't see any other off-diagonal peaks for that narrow one. Yeah?
So is the size of the dot kind of related to like the J coupling?
Yes. Because the more J coupling and the larger the J coupling, the wider essentially the peak will be. So the size of that off-diagonal peak is going to be represented by the size of the width of the signal, essentially, which is influenced by the amount of coupling, I guess. So we're a little bit stuck here, but let's go and start at the other side. Okay, so we originally talked about H is 6, and we said that they should be doublets of doublets and be diastereotopic. Where do you think you would see those in this spectrum?
Oh, it's
3.6.
All the way 3.6 and 3.4, right? So these two peaks here are going to be H6, right? And so H6 and H6, and we see that they couple to each other. All right, so here, let's do it another way. So this is the off-diagonal H2 to H3, showing that coupling. This is H3, no, 3 to H4, right? This is H6 to, say, H6 prime, right? And then notice that both of these H6 primes also go out to here and across, or out here and across. So this part here has to be H5. So this is H6 and H5, and maybe call this H6 prime and H5. Okay, so the tricky part in here that we can't really see because these are so close together, but really there should be an off-diagonal peak here for H4 to H5. Okay, but they're just too close to each other. We can't see that. Okay, so essentially we go, right, from here to here, from here to here, from here to here, from here to both of these over here. Okay, so we can just kind of walk our way around the spectrum, the molecule. Except for these two that are right next to each other. Yeah.
I mean, we got the H6 and H5 just from looking at the molecule structure, right? Just because we know.
Well, H6 we basically had because we were looking at the molecule, and because these, from what we looked at before, I would say kind of look like a diastereotopic pair of protons, right? They are kind of, at least the bigger peaks here, they're slightly slanting towards each other. But notice, well, the big couplings are slanting towards each other. And then notice these small couplings are slanting this direction. At least on this one, see these two peaks here? And those two there are slanting, saying they're coupling over here. These are more horizontal because they're farther away from H5. And so these are more first order, the small coupling. These are slightly second order. All right? Okay, so let's look at another example. Okay, so this is a slight variation of experiment. So this is called a COSY 45 experiment, which means that that second pulse in the pulse sequence is a 45-degree pulse. Okay, so for one thing, if our second 45 is only, our second pulse is only a 45. For one thing is this is going to be less sensitive because we're not actually tipping all of the magnetization into the XY plane. Okay? But there are some positives here too that, we'll just have to tell what they are.
So why it's less sensitive in cozy 90?
Well, remember when we looked at when we walked through how all of those.
It was a smaller peak.
Right, because remember when either we went. Well, let's go back.
Second slide, I think.
Let's see when we did. It's slightly less sensitive, but the positives here is that it kind of compresses along the diagonal. Meaning that along this diagonal right here, sometimes when we get in close, especially when it's kind of crowded here, there'll be a lot more kind of off-diagonal noise and stuff. Right, so this makes it easier to observe couplings that are close to the diagonal, which we had a hard time on the previous one, right? And the other thing, and I'm not quite sure why this is, but this COSY 45 allows us to distinguish between J2 and J3 couplings. So geminal versus vicinal couplings. Okay, which could be helpful, right? So, and the reason kind of for this is that remember that these J2 coupling constants tended to be negative values and the J3s are positive values. Okay, so, but, in the one-dimensional spectrum, we couldn't tell the difference because all we could do was just measure the difference, and we couldn't tell which side was which or whatever. Okay, so if we look around in this spectrum, we see that some of these are kind of slow, leaning one direction, and some of them are leaning the other direction. Right, the off-diagonal peaks aren't all square or rectangular and symmetrical. They kind of lean, I would say, if I looked at these, I would say maybe this one is leaning this way. That wasn't a very good line. Leaning up this way. This one's leaning this way, but this one is leaning up this way. Okay, so the way that I remember this is that I would say, this is just my head that does this, that this one has a positive slope. It's going up this way, at least in the x dimension. And this translates to, to a negative J value, which means that it is a 2-bond coupling constant. Okay, so that tells us that this off-diagonal peak that has a positive one is coupling between these two, and so these are going to be geminal because they have a 2-bond coupling. So that's a diastereotopic pair of methylene pair. Okay, so if you can see this good enough, we can look around, and not all of them show a lot of slant, but I would say that this one here also has a positive slope. And so that means that this one and this one are also geminal. Okay, because of this one and this one. But the rest of these out here, this, these are all negative slopes, so they're all going to be vicinal couplings. Okay, so I think, let's see if I can see some of these. I think I didn't really work through all of these on this one, but if these are together, we can see that, do those actually go to each other?
2 and 6?
Yeah, so the ones with are 6 prime. Oh, these have, well, 1 and 2 and 6 and 6 prime are all, should all be diastereotopic pairs. And if we look in closer in here, it's a little hard to see if any of those, these seem to be more squared off. And I don't know if that's because the farther off the diagonal they show that more or what. But, you know, it kind of looks like, so this is the most upfield. So the most, I would assume, which do you think would be the most upfield?
2.
Yeah, would be 2, right? So these should be H2. And then presumably because H2 and H2 goes to here, you know, across to here, and also goes across to here, that these two have to be H1.
1 or 3?
Well, 3 is not a CH2 group, right? So it has to be H1 going to H2. And then this down here must be H2 to H3. Right? Because if we go from any of these H2 protons, this one, this off diagonal, and this off diagonal are going to H1. Right? So this is H1, H2, H1, H2. But then there's one more, as we go down here, there's one more off diagonal. And this one is sloping the, you know, this is a vicinal coupling. So from 2, we went back to H1, now we got to go over to H3. So both H2 protons are going into H3 over here, which is, I think, where did I draw that? I think it's this one down here, H3. Which should be, if we look at all of these, it's going to be somewhere in like here. So if we had this blown up and, you know, if you had it on the screen and you could blow it up and you could put cursors and we could probably walk our way through all of this tighter stuff in here too. Though notice that there are some of these that are labeled as, you know, 2 protons here and 2 and 2. And so some of those are overlapping. So it's a little tricky, but you might be able to walk your way through all of that. So let's see. Oh yeah, the other parts here. Where did Yeah. Okay, I think that's enough of that. All right. Everybody got that, though? So let's look at another one. Okay, so this is another Cozy 45. All right, and so I think that we can do a better, I think we can kind of walk our way through this one. Okay, so there's two kind of very similar subunits here. And so where do you think we can look on this spectrum? What stands out to you that we could maybe assign something?
One?
Two.
One is so downfield.
One?
Yep.
But one is a carbon, right? So there's no proton there. Two. So we have two. Let's number these like this. So this, let's say that this is 2 prime, 3 prime, 4 prime, 5 prime, 6 prime. So 2 and 2 prime, right, are kind of similar. They're both on a carbon next to an oxygen and next to a carbonyl. So those should be the most downfield. Right, so can we pick those out in the spectrum then? Yeah. Okay, I'm going to move this up just a little if I can. Okay, so it's these two here. This is, one of them is going to be H2 and one is H2 prime. I'm not sure that we can assign those. Which is which right now based upon their chemical shift. So let's just see if we can go. So these are going to be the H2s. Let's just say that right now. H2s and H2 and H2 prime. Oops. Okay. So let's just go from those. Let's go from this most downfield one. Let's see here. What do we have? What are those? Oh, 3, 2, 2, 3. Oh. Yeah, that's not actually correct. So the thing we didn't, last time, instead of having those acetates on there, they were just alcohols on that other one. So remember that when we have a hydrogen here, if we have just a OH or an ether versus HCO, and if this is an ester, this one actually is more downfield. Okay, so I was wrong. These are not actually the H2s. They're going to be one of these ones that's next to an acetate, so either 3 or 4. Okay, so let's start somewhere else.
6.
6. So 6, oops. 6 next to the amide, or 6 prime, and 6 next to this azide. Those are both CH2 groups. They're just next to a nitrogen. There's no oxygen there. So these should be the two most upfield ones. Okay, and those are going to be CH2 groups that are diastereotopic. Okay, so can we see those? Okay, so they're going to be the most upfield ones, and they should, because this is a cozy 45, they should have a positive slope. So I'd say this one, right? So that means that this peak and this one, oops, is one diastereotopic pair, and maybe positive slope as well. So the other diastereotopic pair would be right here. can we tell, look at those for H6 and H6 prime, those two distereotopic pairs have different coupling though. Notice this one is just two doublets of doublets, and this one are more complicated, right? So can we use that observation to predict which one goes to H6 and which goes to 6 prime?
Yeah. 6 prime is the more complicated one.
Right, because and this is a case where we have a proton on a heteroatom, but it's on an amide, and these exchange less, and so we're seeing some splitting from this amide to the H6 prime peaks. Okay? So the red ones are going to be 6. Oops, gosh, I can't write up high enough there. 6 prime, and the blue ones will be 6. All right, so let's see if we can walk our way around the rest of them. Okay, so let's start with 6 prime. So here's 6 prime. And go down here and over to here. Oh yeah, this is going to be a little... So this has to be H5. Right, so we're going to have a 5 prime in here. Notice here that we're also, let's go to the other one too. So here's H6, and notice if we go to 6 and across, it also overlaps there. But if we look at these, notice that these two are slightly offset from these two. Okay? So we have 5 prime, and 5 are overlapped here, but they're not perfectly overlapped, right? And, oops, dang, 5. And the 5 prime ones are slightly more upfield on this end than 5s on this end. Okay? So then when we go from 5 to 4, notice that these two are likewise slightly offset from one another. Okay? So that tells us that this one has to be 5 prime to 4 prime, and this one is 5 to 4. Does that make sense? Okay, so if we go, let's go across from here then, here, and this one looks like it's got, I think it's going to be here. So this is 5 prime to 4 prime. I think that this one, notice this has extra peaks in here too, but I think that goes to this isopropyl group out here, is the more coupled one. There's probably a septet right under there goes for this proton. Okay, so the one to the right side there is the 4 prime, and from here, this goes across to here, and so this is 4 here. All right, so from 4 prime go down to here, to here. This is 3 prime. We go from here this is 3. Then we can go back up this way, past that one to here, or here, and this is going to be 2. And no, that's 2 prime. 2 prime. Dang, I can't. 2 prime and 2. I don't know why. Let's see here. It looks like there's something else. Looks like there's more peaks there, though. Or they're both doublets, I guess. They just have different sizes of splittings.
Are you talking between the 3 and 4?
Yeah, between these peaks. So this is a doublet and this is a doublet. So, but 2 prime to 3 prime and 2 to 3, I guess, have slightly different coupling constants, and so that's why they look a little bit different there.
Between 3 and 4, on the red lines that you pointed towards, it looks like
These two?
2 really close dots.
Yeah, I think that's just, sometimes the close dots just go to like some splitting here. Notice that this one is smaller. So, and I'm not quite sure. It must be just how it looked like the stereochemistry around the ring is the same. But you remember that if this is a vicinal coupling, if somehow it's getting bent closer to 90 degrees, then there won't be very good coupling. So there may be an angle dependence there. Okay, so let me finish drawing these in, though. So it was from this side of this, goes to that, and from this side of this goes to here. Okay, so we're just able to walk our way around both of these molecules and do all of the assignments. Yeah, see? Which is more than we could get just looking at the one-dimensional spectrum, right? But we're still in a pretty good shape here because most of these, except for 5 and 5 prime, most of them are pretty well resolved, right? So that, makes it good. This is a case where you might run this spectrum and in my luck, probably, all of these peaks or something here would all be right on top of each other. But then that's where you could go and you could maybe try a different solvent and maybe they're going to move apart better. So you could play around with that. So yeah, let's just stop there. And we'll look at some more examples on Wednesday.